Welcome to today's Oracle Machine Learning Office Hours feature highlight, using R to cluster data at scale in Autonomous Database. I'm your host, Mark Hornick, joined by Cheryl LaMonica, and we welcome our guest speaker, Nick Cusado. Nick is a solution engineer working from the North America Specialist Hub, focusing on data management. And in this session, we continue our preview of Oracle Machine Learning for R on Autonomous Database. Nick has contributed to the soon-to-be-released OML for R clustering notebooks, and these new template examples will be available with Autonomous Database when OML for R is released. After introducing some clustering concepts, Nick will walk us through a demonstration of in-database clustering algorithms using OML notebooks. And as always, if you have questions, please post them in the Q&A, and we'll address these either during the session or at the end. Let's take a quick poll of your primary objective for today's session. Is your goal to learn about the basics of clustering, understand how to cluster data using in-database algorithms, get a preview of OML for R on Autonomous Database, or something else, which you can specify in the Zoom chat? So let's start the poll. Okay, so we see a number of folks wanting to get a preview of OML for R on Autonomous Database. We have an even split there between learn about the basics and understand how clustering works for in-database algorithms. Looks like we've got a pretty even split now across all of them. All right, well, thank you for responding to our poll. And with that, I will turn it over to Nick.
Thank you. Good morning and good afternoon, everyone. I hope you're having a great day so far. My name is Nicholas Casado, and I am a solution engineer based out of the Santa Monica office for NASH, North America Specialist Hub. And yeah, Mark Hornick has actually trusted me with working on creating some of these template notebooks as a team for the newest release, OML for R, and along with Miles, in case you had caught the previous week's office hours. And I've had the pleasure to dive deep into the clustering algorithms for Autonomous Database using R programming. And as I mentioned in the abstract for the presentation, I've worked on a fun and lighthearted way of explaining Oracle's ability to scale these complex machine learning techniques. And if you also managed to read the abstract, then you might know that I wanted to color this topic with an example from a current event. I'm going to get started. So most recently, NASA's James Webb telescope revealed some astonishing new images of our universe, some never before seen details of a galaxy group called Stephan's Quintet. And as you can see here, there is a lot of detail about 150 million pixels in the raw image, which is a composite of 1,000 separate image files. And to add some more background on this topic, Mark actually had shown up to one of our meetings with his Zoom background as this image, which spurred some conversation. Like, one of the main questions asked was like, what defines the clusters for each of the 5 galaxies from which the name comes from, Quintet? Like, where's one start and the next end? This brought up an even better train of thought. Like, it's relatively easy to see clusters in 2 or 3 dimensions, dimensional images. But what happens when we're confronted with significantly more dimensions, from like 10 to 100, scaling to demand for like realistic situations? We need advanced clustering algorithms to differentiate between this sort of pile of data and the future for the direction of space exploration. Now, I get started. I have a lot to cover. First, I want to give some background on clustering algorithms, and then going into some comparison between the techniques, starting with K-means, and then expectation maximization and orthogonal partitioning clustering. And then the review of the notebook template, and then we'll finish up with the short conclusion. Now, I want to show you what we've been working with to give some more context to this image. So I'm going to break out this PowerPoint into the OML notebook to show some visualizations. Here's our OML notebook. Post that image. This is our Galaxy notebook. And first, we created a demo data set. I set a seed here so it's consistent. And I made this persistent using ORE create for some more context later using SQL Developer's Data Miner. But now if we plot this data right here, we get a similar visualization to the 5 clusters. You can sort of differentiate. Now pushing this in database, we are working with in database algorithms. So we're going to build, score, and visualize with K-means. And there's a distinction of K-means and the other two, specifying the number of clusters desired. We'll get into that more later. But so if we set the number of centers and specify a specific name, as you can see here, I gave it galaxy clustering model. And this will come up for data miner as we want to pull that information later for a hierarchical tree. Now, if we run our predict, we can start to assign values to the clusters, as you can see here, showing a head function and then plotting to see how they match. So we're going to scroll to the visualization. Now it picked up those pretty quickly. With K-means, we specified we wanted 5 clusters, and we got 5 clusters, as you can see here. And the centroids are marked in white. Now let's make a note of these scoring values right here. As when we look at the hierarchical tree, it'll make sort of more sense. So I'm going to break back into this. Right, so this is from data miner, and I was able to grab this tree just from that data that we saved. Pretty interesting. It shows the root and each of the 5 clusters. And there's leaves and parent and child relations, so you can sort of make sense of that in abstract detail. But we can sort of make note of these ranges, the 3 and the 4s. And so as we go back to this demo environment, you can sort of make some visualizations saying the probability of this head is in cluster 6, as there are most in cluster 6, as you can see here. And we do that comparing sort of the raw data and the class data and the tail as a. Now, this is where it gets interesting. I used O clustering for the same quintet data set. And here we specify the upper range. So as I go up to here, this number of centers, that's the upper limit for the clusters. We can see some details, some of the settings here. We'll get into that more later. But as if I go into the output, you can notice that it sort of consolidates some of these clusters into 3. Because as an upper limit, it doesn't put a function there. You can see a centroids in black in the colors. It's quite distinct between the outcomes, but we can jump into why. So I'm going to turn back to the PowerPoint for more context. All right, so clustering algorithms have a lot of unique possibilities in applications, and some of these might surprise you. First, the obvious in business. We are often customer focused, so segmenting customers for targeted marketing can determine the success for any sort of campaign. So we want to know where the most effective our time is spent. And then anomaly detection is actually a great for fraud prevention, from auto to healthcare, insurance fraud detection. It's a multi-million-dollar business and can have a huge impact on large businesses. And we can also make recommender systems, which can be used, say, for fantasy football or sports like March Madness. There are spam filters, which identify junk email avoid those phishing attacks that we're so afraid of. And clustering is also a part of network traffic, classifying alert data. Enterprise IT components actually generate a large amount of alerts, which can really bog down operations. So automatic screening of alerts can prioritize some of this downstream processes. And then clustering could be used for categorizing documents using tags and topics to represent each document as a vector and term frequency to sort of classify this document. Really interesting stuff. And there's a bunch more of unique implementations that I really have time to go into, but highly recommend looking into it if you're interested. So on the next slide, I'm going to go into some background. So to start off, clustering as we know it, it finds data objects, categorizes them based on similarity to each other. And this process has a long history, starting with anthropology in the 1930s, where Driver and Kroeber were attributed for this conception. And the algorithm, however, which is most popular, Kmeans, was originally discovered by the Polish mathematician Hugo Steinhaus in 1956. And he introduced his algorithmic clustering approach in a French paper sur la division des corps multiplication parties. I hope I didn't butcher that, but he named it bagging predictors, which kind of makes sense as clustering, bagging predictors. It's pretty fun. Well, AEM, expectation maximization, was conceptualized in 1977, while OC, which is proprietary to Oracle, is much more current. So let's get into a little bit of a simple demonstration. All right, so for our examples, they're classified as density-based, distance-based, and grid-based, simplistically, and which we can designate as we go, but a couple more important designations include hard clustering and soft clustering, which you can see these two clusters are hard as they're separate, and then these two are soft as they kind of overlap. Now, another is designation of method. It's helpful to see how OML improves on conventional thinking. Normally, K-means is partitioned, meaning that the data is split randomly, which makes it sensitive to random selection of initial centroids. But versus nested here, you can see, which seeks to build a hierarchy of clusters, which we'll get into that more later. But it's important note to understand how OML is sort of improving on conventional approaches. Now, I hope that's easy to understand. Please send any questions in the chat. If not, all right, so let's dig into this and start a really simplified version of K-means in 1D. All right, so here is an array of some random points along its axis. And first, I want to apologize if anyone has any color sensitivities. This might be difficult to see if you're able to distinguish between colors, but let's get started. So first we need to do is identify the number of clusters we want. So for K-means, this is the value of K. We want 3 clusters, so we pick 3 data points. And in order to start assigning points to clusters, we need to measure the distance from the first point to each seed. And we're going to assign the shortest distance to the nearest cluster, as you can see here. We are going to continue for each point, measuring these distances for the next assignment with respect to each of the seeds. So now this one is green, and we can skip to assign the last to the closest cluster at the end. And then we want to, now that we've assigned all the points, we want to take the mean values for all the clusters. And then we can assess the quality of the clustering by taking a summation of the variation. And then if we add up each of the cluster ranges, this is our first attempt. K-means is an iterative process. So if we use new centroids that we averaged with the previous cluster and assign points so we can measure and compare the variation summation. If we can see the centroids don't actually move much, if we did that, if we grab new ones, that's the kind of limitation in this sort of simplified version. But with more dimensions, there's more room for movement. But typically with clustering, there's different stopping criteria, like specifying the number of iterations, or if the centroids aren't moving, it'll automatically have this control mechanism in place so we don't waste our effort. And we can see that this first attempt is the winner for having the least amount of variance. Now, to reflect on the first example I showed you in the Galaxy Notebook, determining the number of clusters can be difficult, especially since k-means is dependent on the assignment of k, and variance can be optimally decided upon. As you can see here, the single cluster has the most variance, going down as the number of clusters increases. Then there becomes a point in which there's no trade-off and we lose sight of the whole objective as a whole. So algorithmically, there are ways to determine this, like the elbow method. Conceptually is an easy way to decipher the number. It's not necessarily the best method in comparison to, like, say, silhouette or the gap statistic, but elbow is the easiest to implement. And I'd recommend reading we have a great blog on blogs.oracle for more information. Here's a link. And like I mentioned before, each of these database clustering algorithms have different characteristics and behaviors. So maybe k-means number of clusters is predetermined, right? As I mentioned, EM and OC are automatically determined. So that is based on how they are calculated. So EM is density estimation, which I'll show in a second, while OC is a proprietary grid-based system that also works off of a density estimation. And each of these are suited for any size data set, where O clustering uses adaptive sampling for large samples, large data sets. And lastly, attribute importance is important designation for choice in algorithm. And these mostly are distinct. So EM works with both high and low. K-means is better for low, and OC is better for a high number of attributes. This is just a quick glance, as there are other criteria for comparison, but I figure I'd give you a quick taste of what's to come. So let's illustrate these differences. So first, EM features this sort of soft clustering approach mentioned on. It's the density-based approach. So I'm not going to go into the mathematics of all, but it determines the clusters by calculating a Gaussian approach, which allows for some overlap. So these bell shapes you can see here. Now, O clustering is a little bit more complex. So let's look at this 2D example. So here we have a plot comparing income and H. It contains these 3 specific densities, and they are partitioned orthogonally by dividing the grid into density regions as such. And it'll make a little bit more sense if we look at it from a different angle. So where these partitions are made, at the low regions, we are building a hierarchical tree. Now, so we divide, new leaf emerges, and as we divide, it's sort of building this tree, cutting down, pruning based on the density of points. So you'll see in a second. There you go, cutting down, pruning of the tree. And this is what we mean. We're able to eliminate some clusters to ensure this sort of even distribution of assignments. It's sort of a tessellation of the leaves. So once again, if you have any questions, please drop them in the chat. We proceed into the demo portion of this workshop. I've combined some of the templates that were featured in the OML for R debut. So I'm going to just give a quick highlight of what's to come. First, the notebook is focused on k-means. Oops, it's a little bit backwards. There's Kmeans. And we'll go into some of the models. We'll run some EM and O cluster models to illustrate some of these features. And then I will hope that's helpful. I'll show some helpful visualizations to round it all with Galaxy, and some SQL attribute queries. So yeah, jump out of this real quick. Okay, so here's my Kmeans notebook. And as we open the notebook template, we're greeted with a lot of good information, like background information. Like, for example, we're using a customer data set from the SH schema. And if you're familiar with ADB, SH is accessible. The simple query of the database, I'll show you that in a second. But first, we want to import our libraries and turn off some warnings. Now here we have the queries, which we are merging supplementary demographics with customers to add a lot more color to the customer data, to the cust data or E-frame that we're making, and is a proxy using the transparency layer. If we show the head of the data frame, we'll have the key column customer ID right here. And yeah, this sort of merges the two data sets. And since this is only simple data sets, we're going to do a quick dimensions check, and where it has a reasonable 4,500 rows. And now let's get to building the model. So for K-means, we specify the number of centers and the ORE frame that we're working with. So now as an output, we can see all the settings, the number of clusters or iterations. But if we run a summary query, we can see the centers at a quick glance. So here it's similar. And then summary, we have some clusters, centers. So you can see 2, 4, 5. These numbers, 43 for customer age, that first cluster median or mean. Now, here we want to validate these results and view the mean, mode, and variance of those centers. So as you saw before, that 43, there it is again. And because it is a numerical output, there's the variance, which you can sort of gauge that we talked about. That's for cluster 2. Now for sort of categorical strings, they don't really have a variance. So that's sort of in that mode value. And we can explicitly modify, some of these model settings which I've done here in the settings table. And before I mentioned how K-means was an iterative process, we can specify how many iterations you want to do. So there's 20 there. And if we show a summary similar to the default settings, we can see centers. Here there's a minor shift, 43 to 46. And we can view the summary of the clusters where each cluster ID can be better understood. That's down here, but let me jump back. So the summary of the clusters where you can sort of understand these parent-child relations and how many leaves, and is it the dispersion. So I'll get into that a little bit more on the next section, but here we have the sort of hierarchical approach. So like whether the parent is a root or which cluster it belongs to, if it's a leaf or not. Now, here we have this sort of probabilistic assignment for each row. So the first customer right here is a 49%, right? You can see that. And that probabilistically assigns it to cluster ID 5 because it's the greatest, as you can see. And you can sort of see these supplemental columns giving it sort of some context. If we looked at some of the probabilistic detail later. So now if we want to fine tune the model, with some explicit settings. We did that earlier. Now, if we want to run this sort of EM model, here it is. We can show similar results. So we've done 100 iterations. I guess you can see that there. And we can tune a lot of these settings similarly to K-means, but for simplicity, I've just done the default model. And we can assign rows to the clusters, and we can see that the first customer has, well, this sort of right here, you can see it doesn't have the customer ID, but you can make that association from the previous model. 99.9% for cluster 4. So therefore it assigns it to cluster 4. And if we view these centers, we can see a shift in these values. So this one has a 53, which goes even higher. And I guess for K-means it was 43, now it's around 53. Well, customer marital status right here stays about the same, never married. That leaves question, maybe with OC, you'll see a little bit more differentiation. Here's O clustering. In this model, you can specify this sensitivity of the model and the upper limit of clusters. Say here, we have 0.5 and we want 5. And we want up to 5 and we have the maximum output of 5. There it is. And if we look at the cluster assignments, we can see the same sort of probabilistic outcomes for the first customer. So there's the greatest value of 99% for cluster 3. So it gets assigned to the first cluster. And we can see the centers again. Here's that sort of mean mode. And we can see that this sort of mean is even higher. It's 88 for the customer age. And this makes sense because we have higher number of clusters, 81 years old, the higher range of that first one. Now we're going to compare these clusters, and for K-means, we have this first visualization for each of the specific histograms. And say for here, we have the distribution of years of residence for cluster number 3, which has a span up above about 5 years, while the mean is about 3 years. See on the lower end. Well, cluster 5 to the right has a larger span and a higher mean. So we're differentiating between the two. If we look at customer age, we see a higher low end mean, while the cluster 5 mean is around about 60. If you remember O cluster, it had a higher first cluster. Remember that 83, 81. It sort of starts towards the low end. It's all based on this technique of the model, which is an interesting comparison, sort of direction it takes the route. And now lastly, I want to quickly show you how SQL, you can use SQL to highlight the prediction details. Like what are the top factors that contribute most to the factor of this cluster? What are the top predictors affecting the prediction of cluster 5? We have customer age, which has a value of 44 and the highest weight. So that gives it the #1 indicator, and household size, and then customer marital status last with the lower number. Greatest household size, 9+. Now that was it for this notebook. I'm going to jump back to the PowerPoint. I think we have a poll to jump into.
So for our second poll, so how confident are you that you could use in-database clustering? Do you already use it? Are you confident you could use this for clustering data? You're modestly confident but need more experience, or you would like a deeper dive into to this. So let's switch to our second poll. Okay, so we've got, I'd say the majority either want a deeper dive or are modestly confident. And we have a few participants that are confident they could use this for clustering. So that's really great to see. And so probably what we'll do then is have a more in-depth session on clustering, since there seems to be a great deal of interest. So thank you very much for responding.
Thanks, Mark. So as we recap, I want to reiterate the intro. I really simplified the whole process, and I hope that gave you a brief understanding. And OML for ours, very similar. Running some line, very robust, and so with realistic situations, dimensions can scale greatly past the point of visualization. So this quintet galaxy visualization can really help take into account the distance and the centroids and even the hierarchical tessellation of those leaves, which can build this sort of greater understanding of that pile of data, the composite of thousands of images. Now to recap the first question, where do we determine what are the 5 galaxies? And the answer is sort of deterministic to the type of algorithm. So we've created this interesting creative illustrations to highlight sort of these behaviors. So just to sort of generate some images. And so if we choose K-means, we're looking at centroids and sort of iteratively assessing variance while consolidating a parent-child format. You can see here those two middle ones are kind of closest. You can sort of, but with EM, we would look at more of a merged format shown here with overlapping circles and sort of the blending of lines. And with O clustering, we would share this sort of heat map type of view, sort of partitioned cluster domains. And I hope this gives you a good illustration of what sort of brings some mental associations to learning some of these complex in-database methods. So there's a lot more to it, but for this final question, maybe I'll leave that up to you to decide. It's this sort of free-flowing debate on which clustering technique to use and which is the best. With OML for R, we kind of give you options to try them all out and assess which one works best for your data set. So it's really simple to implement and scale with ADB. And we've covered a lot of information. So if you have any more questions that Mark hasn't covered already in the chat, I'd be super happy to hear from him or from any of you if you want to come off mute.
Okay, well, thank you, Nick. That was really excellent. I think that just 2 questions that did come up that we addressed is this notebook that you demonstrated included in the ADW instances? And we will be providing a set of template examples that will be shipped with OML notebooks on Autonomous Database as soon as OML for R is released. And a second question that we invariably get is, when do we expect to release OML for R? And of course, we can't make any specific statements, but it is coming soon, and I encourage you to stay tuned for an upcoming announcement. Otherwise, we had some great feedback from Jared and an anonymous attendee. Very much appreciative of the session. Nick?
Thank you, Mark. And we have some more information here on this last one if you're enjoying these sessions or if you want to learn more. And I definitely appreciate everybody's kind words and questions. So I appreciate the opportunity, Mark. And you've given me a lot of insight and I've learned a lot. So appreciate you all.
All right. Well, thanks again, Nick, and take care, everyone. Until next time.